Today we're going to talk about optimization under uncertainty. So in some optimization problems, certain parts of the data may be uncertain, and we may be making decisions without knowing the uncertain parts of the data, and only after we make the decisions, uncertain parts of the data is revealed to us. For example, we may be buying inventory without knowing what the demand is going to be, and only after we buy the inventory, the demand is revealed to us. Or we may be repositioning drivers to different locations without knowing where the loads are going to be, and only after we reposition the drivers, we get to know where the loads are. So in some optimization problems, some parts of the data may be uncertain. We make decisions without knowing what the uncertain parts of the data is, and only after we make the decisions, we get to see the uncertain parts of the data. In today's lecture, we're going to see how we can model these kinds of optimization problems under uncertainty. So from the perspective of optimization problems under uncertainty, we're going to look at two groups of problems. We're going to look at two-stage problems under uncertainty, and we're going to look at multi-stage problems under uncertainty. In two-stage problems under uncertainty, we're going to make time decisions now without knowing the realization of uncertain quantities. Then the uncertain quantities are going to be revealed to us, and we may make decisions a little bit more after seeing the realization of the uncertain quantities. And our goal is to maximize the total expected reward from the decisions that we make before and after the realization of the uncertain quantities. So that's two-stage problems under uncertainty. We're also going to talk about multi-stage problems under uncertainty. In the multi-stage problems under uncertainty, we're going to make some decisions now, and some uncertain quantities are going to be revealed to us, and we're going to make more decisions. And some other uncertain quantities are going to be revealed to us, and we make more decisions. And then some other uncertain quantities are going to be revealed to us, and so on and so forth. In the multi-stage optimization problems under uncertainty, our goal is to maximize the total expected reward over all the decisions that we make over the whole planning horizon. Okay, good. So let's start by talking about two-stage problems under uncertainty. For the two-stage problems under uncertainty, we're going to use a running example. Here's what our running example is going to look like. So let's imagine that we're managing a reservoir, we're managing a dam, we're managing the water supply in a reservoir during the month of June. Okay, we're managing the water supply in a reservoir during the month of June. At the beginning of month of June, let's say we have 150 units of water in our reservoir. At the beginning of month of June, we decide how much water we're going to release from our reservoir. And the water that we release from our reservoir is being used by farmers for irrigation purposes. So for each unit of water that we release from our reservoir, we're going to incur some revenue. Let's say for each unit of water that we release from our reservoir, we're going to generate a revenue of $3. So now after that, after we decide how much water we're going to release from our reservoir, after that, we're going to observe the random rainfall during the course of June. And that's going to take us to the end of June. And at the end of June, we're going to look at how much water we have in our reservoir. And the water that's left in the reservoir at the end of June is being used by recreational purposes. And if the water left in the reservoir at the end of June is below a desired level, then we're going to incur a penalty because the people are not going to be getting the recreational benefits that they want at the end of June. And let's say for every unit of short, we are below 100 units in our reservoir, we're going to incur a penalty cost of $5. And our goal is to figure out our goal is to figure out at the beginning of June, how much water we should be releasing so that we maximize the total expected profit during the month of June, and the total expected profit being the revenue from the water release minus the expected penalty cost of not being able to provide the recreational benefits. So this was a lot of English, so let's try to write some things down so that things become a little bit more concrete, a little bit more clear. We said two-stage problems under uncertainty. Two-stage problems under uncertainty. Here's what the timeline of events are going to look like. Okay. This axis we drew is the time. So let's say this is the beginning of June. This is the end of June. Great. At the beginning of June, the first thing we do is we observe the current water level in our reservoir. observe the current water level. Let's say the current water level in our reservoir is 150 units, whatever those units are. And after that, we decide how much water to release from the reservoir during the course of June. Decide how much water to release during June. And each unit of water that we release from the reservoir, we're going to have some irrigation benefits. So for each unit of water that we release from the reservoir, we're going to make $3. For each unit of water released, make $3. Good. And then we're going to observe the random rainfall during the course of June. And let's say the random rainfall during the course of June can be low, medium, high. And the low rainfall corresponds to getting a rainfall of 125 units. Medium rainfall corresponds to getting a rainfall of 200 units. And high rainfall corresponds to getting a rainfall of 300 units. So after we decide how much water to release from the reservoir during the month of June, we get to observe the random rainfall. Observe random rainfall. And the random rainfall could be low. And if we get the low rainfall, we're getting rain for 125 minutes. And the probability of getting low rainfall is, let's say, 0.3. Or the rainfall could be medium. If you get medium rainfall, we get rainfall for 200 units. And the probability of getting medium rainfall is 0.5. Or we could get high rainfall. If we get high rainfall, we get 300 units of rain, and the probability of getting high rainfall is 0.2, so that these probabilities are adding up to 1. Okay, so now you observe the random rainfall. And at the end of June, we observe the water level in our reservoir. Observe the water level at the end of June. And for each unit of short, we are below 100, we're going to have a penalty cost of $5 because, again, the people are not getting their recreational benefit at the end of June. So having too little water in our reservoir is problematic. For each unit of water, we are short of 100 units, incur penalty of $5. And our goal is to decide how much water we should be releasing from our reservoir. Our goal is to decide at the beginning of June how much water we should be releasing from our reservoir so that we maximize the total expected profit during the month of June. And again, the total expected profit being the revenue from the released water minus the expected penalty cost that we incur at the end of the month. Okay, so let's again recap the dynamics of the problem. At the beginning of the June, the current water level in our reservoir is 150 units. Then at the beginning of June, we decide how much water we should be releasing during June. And for each unit of water that we release during June, we make $3. Then during the month of June, we observe the random uncertain rainfall. The rainfall could be low, medium, high with these quantities and with these probabilities. Then that takes us to the end of June. At the end of June, we observe the water level in our reservoir at the end of June. And if the water level in our reservoir is below 100 units, then for each unit we are short below 100 units, we incur a penalty cost of $5 because the people are not getting the recreational benefits that they want. Okay, and our goal is to figure out how much water, our goal is to figure out at the beginning of June how much water we should be releasing so that we maximize the total expected profit during the month of June. Okay, so that's the problem we're interested in. Good. So the first thing we're going to do is we're going to draw some kind of a scenario tree that captures the revelation of the uncertain quantities over time. Okay. So here's what that scenario tree is going to look like. So now in the vertical axis, let's draw the time. In the vertical axis, let's draw the time. So this is the beginning of June. This is the end of June. Good. And let me put a box on the top. that represents the state of the world at the beginning of June. This box represents the state of the world at the beginning of June, and we had 150 units of water at the beginning of June. Okay. And then we decide how much water we should be releasing from our reservoir during the month of June. And after that, the rainfall could be low, medium, high. So I'm going to put 3 boxes at the end of June that corresponds to the state of the world when the rainfall is low, medium, and high. So here's a box at the end of June corresponding to the state of the world where the rainfall during June turned out to be low. Here's a box at the end of June corresponding to the state of the world when the rainfall during June turned out to be medium. And here's a box at the end of June corresponding to the state of the world when the rainfall during June turned out to be high. So we come to this box if the rainfall is low, we come to this box if the rainfall is medium, we come to this box if the rainfall is high. So this is low rainfall, medium rainfall, high rainfall, and low rainfall. Low rainfall has a quantity of 125, probability of 0.3. Medium rainfall has a quantity of 200, probability of 0.5. High rainfall brings a water of 300 units, probability of 0.2. Okay, good. So let's also label these nodes. So let's say this is labeled A. This is node A, B, C, D. Good. The next thing we're going to do is, at each one of these nodes, we're going to think about what decisions we make. Okay. This is the state of the world at the beginning of June. This is the state of the world at the beginning of June. That's the state of the world at the beginning of June. And the water level in our reservoir at the beginning of June is 150 units. What is the decision we make at the beginning of June? The decision that we make at the beginning of June is how much water to release. Let's use a decision variable, x sub a, to denote how much water we decide to release at the beginning of June. So our decision variable x sub a denotes how much water that we release at the beginning of June. Good. Then when we come to node B, which is going to be the state of the world at the end of June, given that rainfall turned out to be low. When we come to node B, this is the state of the world at the end of June, given that rainfall turned out to be low. This is the state of the world at the end of June, given that rainfall turned out to be low. We're going to observe the water level in our reservoir, and we're also going to check how much we're short below the desired level of 100 units. So let's use decision variables YB to denote the water level in our reservoir at the end of June, given that rainfall turned out to be low. And let's use the decision variable ZB to denote the shortage at the end of June, given that the rainfall turned out to be low. Let's write those quantities. Let's write those decision variables. We said X sub A is the water level, water released at node A. So this is the amount of water that we decide to release at the beginning of June. Good. What is decision variable YB? The decision variable YB is the is the water level given that we're at node B. In other words, YB is the water level given that the water level at the end of June, given that rainfall turned out to be low. Okay, so YB is the water level at node B. In other words, water level at node B. In other words, YB is the water level at the end of June, given that rainfall during June turned out to be low. So YB is the water level at node B. In other words, this is the water level at the end of June, given that rainfall turned out to be low. And what was ZB? ZB is the amount short we are at the end of June, given that the waterfall during June turned out to be low. Amount short, let's say at node B. ZB is the amount short at node B. In other words, amount short at the end of June, given that rainfall turned out to be low. We also define decision variable YC and ZC. What is YC? YC is the water level in node B. In other words, YC is the water level at the end of June, given that rainfall during June turned out to be medium. What is ZC? Shortage at node C. In other words, ZC is the shortage at the end of June, given that rainfall turned out to be medium. And let's also define the decision variable YD and ZD. What is YD? YD is the water level at node D. In other words, YD is the water level at the end of June, given that rainfall during June turned out to be high. What is ZD? ZD is the shortage quantity, shortage amount in node D. In other words, ZD is the amount we're short at the end of June, given that rainfall during June turned out to be high. Let's write similarly for YC, ZC, YD, and ZD. Okay, so we have 1, 2, 3, 4, 5, 6, 7 decision variables. Let's construct our objective function. Let's construct our objective function. Let's construct our objective function. For each unit of water that we release, we make a revenue of $3. For each unit of water that we release, we make a revenue of $3. We're releasing XA units of water. We're releasing XA units of water from our reservoir. So the revenue that we make is 3 times XA. Good. Then at the end of June, for each unit we're short, we incur a penalty cost of $5. At the end of June, for each unit we're short, we incur a cost of $5. So at the end of June, if I'm in node B, at the end of June, if the rainfall turned out to be low, at the end of June, if I'm in node B, at the end of June, if the rainfall turned out to be low, the amount I'm short is ZB. So now my shortage cost is going to be 5 times ZB. But what is the probability of reaching node B? It is 0.3. So the expected cost that I incur in node B is going to be 5 times ZB times 0.3. That's the probability of reaching node B. Likewise, at the end of June, if I reach node C, at the end of June, if the rainfall turned out to be medium, I reach node C. At the end of June, if the rainfall turned out to be medium, the shortage I incur is ZC. So then the shortage cost is going to be 5 times ZC. And the probability of reaching node C is 0.5. That is the probability of getting medium rainfall. Okay, so this is the expected shortage cost from node C. And likewise, if I end up in node D, the shortage cost is 5 times ZD. The probability of reaching the node D is 0.2. Okay, so this is the revenue that we collect from the water release. This is the penalty cost due to being short at the end of the month. That is the total expected profit. That is the total expected profit over the whole planning horizon. And we say the expected profit because our revenue is deterministic, but the cost that we incur is random. It depends on how much rainfall that we incur, that we observe. Okay, so then this objective function is what? 3xa minus 1.5 ZB minus 2.5 ZC minus 1 ZD. That's the objective function. Great. Next thing we're going to do is we're going to think about the constraints. In particular, we're going to write constraints that relates the water level at the end of June to the water level at the beginning of June and how much water we release and what the rainfall turned out to be. Let's say it again. We're going to write some constraints that relates the water level at the end of June to how much water we had at the beginning of June, what water we released, and how much rainfall we got. Like, for example, what is the water level in our reservoir at the end of June, given that rainfall turned out to be low? What is water level at the end of June? What is water level at the end of June in our reservoir, given that rainfall turned out to be low? So that's YB. YB is the water level in our reservoir at the end of June, given that rainfall turned out to be low. That is given by how much water we had at the beginning of June, minus how much water we released, plus how much rainfall we got during the low rainfall scenario. That is 125. So this is a constraint that relates the water level at the end of June under the low rainfall scenario to the water level at the beginning of June and how much water we decided to release. Good. Next thing we're going to do is we're going to compute the shortfall. We're going to compute the short at the end of June as a function of the water level at the end of June. In particular, if the water level at the end of June is above 100, we don't have any shortage. If the water level is at the end of June is below 100, we're going to have shortage. Okay. So if the water level at the end of June is less than 100, then the amount we're short is equal to how much ever we're short, 100 minus YB. And if the water level at the end of June is above 100, then the amount we're short is going to be 0. Okay, so I want to write constraints that ensures that if the water level at the end of June is less than 100, then the amount we're short is 100 minus the water level. If the water level at the end of June is less than 100, then the amount we're short is 100 minus the water level. But if the water level at the end of June is greater than 100, then the amount we're short is 0. So we're going to write constraints that ensures this relationship. Let's write that. In our objective function, we're going to maximize this objective function. We're going to maximize this expected profit. So if you want to maximize this expected profit, we're going to make ZB as small as possible, right? In our objective function, we're going to maximize this expected profit. If you want to maximize the expected profit, we're going to make ZB as possible. So then, to get this relationship where our shortage is 0, if the amount of water is greater than 100, and our shortage is 100 minus YB if the amount of water is less than 100, let's write a constraint that says the following. ZB is greater than or equal to 100 minus YB, and ZB is greater than or equal to 0. And let's see what this constraint is going to do. Let's look at the case where the water level at the end of the month, is 180, so that we do not have any shortage. Okay. So if the water level at the end of the month is 180, so the right-hand side of this constraint is going to evaluate the minus 80. 100 times minus 100 minus 180 is minus 80. The right-hand side of this constraint is 0. And by the objective function, we said we're going to make ZB as small as possible. If we're pushing ZB as low as possible, while saying that ZB is greater than or equal to minus 80 and ZB is greater than or equal to 0, this is 0, this is minus 80, this is 0, this is minus 80. I'm pushing ZB as low as possible. This is 0, this is minus 80, this is 0, this is minus 80. I'm pushing ZB as low as possible while making sure that ZB is greater than or equal to minus 80 and ZB is greater than or equal to 0. ZB is going to get stuck at 0. So then if YB is equal to 180, indeed, with these two constraints and by pushing ZB as low as possible, ZB is going to be exactly equal to 0, and that's exactly what we want. If YB is greater than or equal to 180, if YB is greater than or equal to 100, ZB should be 0. On the other hand, let's look at the case where the water level we have in our reservoir at the end of the month is 80. So we have some shortage. So then what is the right-hand side of this constraint? 100 minus 80, it is 20. The right-hand side of this constraint is 0. Again, by the virtue of this objective function, we're pushing ZB as low as possible. So I'm pushing ZB as low as possible while making sure that ZB is greater than or equal to 20 and ZB is greater than or equal to 0. Here's 20, here is 0, here is 20, here is 0. We're pushing ZB as low as possible while making sure that ZB is greater than or equal to 20 and ZB is greater than or equal to 0. If I push ZB as small as possible, while making sure that ZB is greater than 20 and ZB is greater than 0, ZB is going to get stuck at 20. So then indeed, if YB is equal to 80, if the water level at the end of the month is equal to 80, then ZB is going to get stuck at 20. So indeed, if the water level in my reservoir at the end of the month is less than 100, then the shortage is going to be 100 minus the water level. Okay, so then these two constraints, by the virtue of we're also trying to make ZB as small as possible in the objective function, these two constraints are going to ensure that if the water level is less than 80, then our shortage is going to be 100 minus YB. I'm sorry, if the water level is less than 100, our shortage is going to be 100 minus the water level. If the water level is greater than 100, our shortage is going to be 0. So these constraints are going to compute the shortage quantities exactly as we want. Now let's write the other constraints that we need. So this constraint relates the water level at the end of June under low rainfall scenario to the water level at the beginning of June and how much water we release. Likewise, we're going to relate the water level at the end of June under the medium rainfall scenario to the water level at the beginning of June and how much water we release. So let's write those constraints down. YC is given by how much water, the water level at the end of June under medium rainfall scenario is how much water we had minus how much water we released plus how much rainfall we got under the medium rainfall scenario. And what else? I want to compute my shortage quantity as a function of, I want to compute my shortage quantity in node C as a function of the water level in node C. So we're going to write the constraint ZC is greater or equal to 100 minus YC, and ZC is greater or equal to 0. And let's do the same thing for node D. Let's compute the water level in node D. The water level at the end of June under high rainfall scenario is whatever we had at the beginning of June minus what we let flow out of the reservoir plus the rainfall. Okay, and likewise, let's compute the shortage at the end of June under high rainfall scenario as a function of the water level at the end of June. 100 minus YD, CD is greater or equal to 0. So then we have all the ingredients of our optimization problem. Putting it all together, in our optimization problem, we're going to maximize this expected profit function subject to this constraint, this constraint, this constraint, this constraint. So that's our optimization problem. Let's write it down so that we have a full formulation. Our optimization problem is given by maximize this objective function 3xa minus 1.5 ZB minus 2.5 ZC minus ZD subject to this constraint. YB is 150 minus XA plus 125. ZB is greater or equal to 100 minus YB. And I'm going to write the non-negative constraint later. YC is equal to 150 minus XA plus 200. ZC is greater or equal to 100 minus YC. Okay. And I'm going to write the non-negative later on. And YD is given by 150 minus XA plus 300. And ZD is greater or equal to 100 minus YD. And then all of our decision variables are non-negative, namely XA, YB, YC, YD, ZB, ZC, CD, they're all negative. So this is the optimization problem. Okay. One important thing that we're going to emphasize is how much water I have at the end of June under each one of the rainfall scenarios depends on the single release quantity that we determine at the beginning of June. How much water that we end up with at the end of June under every possible rainfall scenario depends on the single release quantity that we decide at the beginning of June. So as a result, all of these YB, YC, YD, ZB, ZC, ZD variables are all determined in one optimization problem because they are all dependent on the same XA decision variable. Okay. If you solve this optimization problem, if you throw it to Groby, you get the optimal solution. And actually, if you indeed solve this optimization problem, the optimal solution turns out to be the following. The optimal solution is XA is given by 250, YB is given by 25, ZB is given by 75, YC is 100, ZC is 0, YD is 200, ZD is 0. What that means is, at the beginning of June, we decided that we're going to release 250 units of water from our reservoir. At the beginning of June, we decided that we're going to release 250 units of water in our reservoir. If the rainfall turns out to be low, then at the end of June, I'm going to get stuck with 20 units, 25 units of water in my reservoir, which means that I'm going to be short 75 units. But if rainfall turns out to be medium or high, if the rainfall is medium, I'm going to have 100 units of water in my lake. So in that case, I'm not going to have any shortage. And likewise over here, if the rainfall turns out to be high, I'm going to have 200 units of water in my reservoir. I'm not going to be short. So I decided to release 250 at the beginning of June. And if rainfall turns out to be low, I'm willing to take the hit. I'm taking a gamble. Okay. But the cost that I incur from that gamble is justifying the revenue that I collect from the water I release. So this is the optimal solution. Release 250. If the rainfall turns out to be low, you're going to incur shortage in your reservoir. But if the rainfall turns out to be medium or high, you're not going to incur shortage. Okay. So this is how we modulate decision-making problem, optimization problem under uncertainty that takes place in two stages. We make some decisions now. We observe the realizations of some random quantities, and then we make some other decisions. And our decisions at the end of June was pretty trivial. We just measured the level of the reservoir. It wasn't really too much of an interesting decision. Okay, so this was the decision-making problem, optimization problem under uncertainty in two stages. So now let's talk about optimization problems under uncertainty that takes place over multiple stages. We're going to continue our running example, but now, instead of managing the reservoir over a single month of June, let's manage the reservoir over 3 months during the summer, okay? So now we're going to manage the water in our reservoir during the months of June, July, and August. And here's how the problem is going to progress. At the beginning of June, we have 150 units of water in our reservoir. So at the beginning of June, we decide how much water we should be releasing from our reservoir in June. And then for each unit of water that we decide to release, we're going to make $3. Then we observe the rainfall, random rainfall during the month of June. That takes us to the end of June. At the end of June, we measure the water level in our reservoir. If we're short below the desired water level of 100 units, then we're going to incur the penalty cost at the end of June. So now that takes us to the beginning of July. At the beginning of July, I'm going to play the same game again. At the beginning of July, I'm going to decide how much water we should be releasing from our lake during July. Then we're going to observe the random rainfall during the month of July. That's going to take us to the end of July. And at the end of July, we're going to observe the water level in our lake, in our reservoir at the end of July. Again, at the end of July, if we're short, below the desired level of 100 units, we're going to incur the penalty cost again. That's going to take us to the beginning of August. At the beginning of August, we're going to decide how much water to release from our reservoir during August. Then we're going to see the random rainfall during the month of August. That's going to take us to the end of August. At the end of August, we're going to observe how much water we have in our reservoir. And if we're short below the desired level of 100 units, we're going to again incur the penalty cost of not providing the recreational benefits. And our goal is to figure out how much we should be releasing from our reservoir over the course of the planning horizon so that we maximize the total expected profit. And the total expected profit is given the water that we release in each one. Total expected profit is given by the revenue from the water that we release in each one of the months minus the expected cost of not providing the recreational benefits. Okay. So let's try to formulate this problem. Multi-stage problems under uncertainty. Okay, let's again draw a timeline of events that's going to make sure that we understand the problem description. I'm going to draw a longer line because now I have 3 months. Okay, so these are dark ticks. So this is the beginning of June. This is the end of June, beginning of July. This is the end of July or beginning of August. And this is the end of August. Good. At the beginning of June, we have 150 units of water in our reservoir. Observe water level of 150 units. Good. And then we decide how much water we should be releasing during the month of June. Decide how much water to release during June. And for each unit release, we're going to collect the revenue of $3. Okay. Then we're going to observe the random rainfall during the course of June. Okay. And let's say the random rainfall could only take low and high values. So the random rainfall could be low, and low rainfall corresponds to 125 units coming into our reservoir, and it happens with a probability of 0.4. Or the rainfall could be high, and high rainfall brings a rainfall of 300 units, and it happens with a probability of 0.6. So let's only put two rain scenarios. And that's going to take us to the end of June. At the end of June, we're going to look at how much water we have in our reservoir. And then we're going to incur $5 of penalty cost for each unit we're short. Observe the water level, and let's say incur penalty cost of $5 for each unit short. Good. So then that is going to take us to the month of July. So in the month of July, we decide how much water to release during July. Decide how much water to release during July. And then we're going to observe the random rainfall during July. Let's also assume that the rainfall during July can be low and high with the same quantities and with the same probabilities. So that takes us to the end of July. At the end of July, we're going to observe the water level, and we're going to incur the penalty cost if we're below the desired level of 100 units in our water reservoir. Let's say observe water level, incur penalty cost if short. Good. And that takes us to the beginning of August, and the game is going to continue. At the beginning of August, now we have the water level at the end of July or the beginning of August. We decide how much water to release in August. And now you observe the random rainfall during August. That takes us to the end of August. We're going to observe the water level at the end of August and incur the penalty cost if we're short. Observe water level and incur penalty cost if short. Good. Okay, let's again make these ticks clear so that this is 1 month of June. And now we have July and we have the August. So this is the sequence of events. Good. So we start from the beginning of June with 150 units of water in our reservoir. We decide how much water we should be releasing during June. Those gives me some revenue. We observe the random rainfall. That takes me to the end of June. And I observe the water level in my reservoir at the end of June. And if I'm short, I incur my penalty cost. So now I'm at the beginning of July. I again decide how much water is released during July. I observe the random rainfall during July. Now at the end of July, if I'm below the desired level of 100 units, for each unit I'm short, I'm going to incur another penalty cost at the end of July. Now at the beginning of August, now I decide how much water to release during the month of August. I observe the random rainfall. That takes me to the end of August. At the end of August, I look at how much water I have in my reservoir. If I'm short at the end of August, I'm also going to incur a penalty cost at the end of August. And we're figuring out how to make our decisions to maximize the total expected profit over the course of the 3 months. Good. So now what we're going to do is we're going to again draw a tree. We're going to draw a tree that captures the states of the world under different relations of the random rainfalls. Okay? We're going to draw a tree that captures the states of the world under different realizations of the random rainfall. So let me put again the time on the vertical axis now. Okay. So this is the beginning of June. This is the beginning of June. This is the end of June or beginning of July. This is the end of July, beginning of August. And this is the end of August. Great. Good. So my problem is starting at the beginning of June. Let's put a box over here that represents the state of the world at the beginning of June. Okay? And we start with 150 units of water in our reservoir. So then, during the month of June, the rainfall could be high, the rainfall could be low. There are only two possible realizations of the rainfall. So let's put two states of the world here. So this is the state of the world at the end of June. Given that rainfall during June turned out to be low, this is the state of the world at the end of June, given that rainfall during June turned out to be high. This is the high rainfall, this is low rainfall branch, and low rainfall again corresponds to a quantity of 1.25. It happens with a probability of 0.4. High rainfall corresponds to a quantity of 300. It happens with a probability of 0.6. Again, this is the state of the world at the end of June or the beginning of July. Given that rainfall during June turned out to be high, this is the state of the world at the end of June. Given that rainfall during June turned out to be low. Good. So now let's put two boxes underneath this box. So rainfall in July can be low or high with the same probabilities and the same quantities, we said, to make things easier. So now what is this? This box is the state of the world at the end of July, given that rainfall during July turned out to be low and rainfall during June turned out to be low. This is the state of the world at the end of July or the beginning of August. This is the state of the world at the end of July, given that rainfall during July turned out to be high and rainfall during June turned out to be low. Likewise, let's replicate these boxes here. Low, high. What is this box? This is the state of the world at the end of July, given that rainfall during July turned out to be high and rainfall during June turned out to be high. You get the idea? And let's finish our diagram. low, high, low, high, low, high, low. Good. So one last time, what is this box represent? This is the box that represents the state of the world at the end of August. Given that rainfall during August turned out to be high, rainfall during July turned out to be high, and rainfall during June turned out to be low. You get the idea. So now let's label each one of these boxes. Node A, node B, node C, D, E, F, G, H, I, J, K, L, M, N, O. Good. Now we're going to associate some decision variables with each one of these boxes. Okay. At the beginning of June, what is the decision I make? At the beginning of June, the decision I make is how much water I release during the course of June. Let's use the decision variable x sub a to capture that. Okay, good. In node B, this is what's happening at the end of June. At the end of June, this node B. Node B corresponds to the end of June or the beginning of July. Node B corresponds to the end of June or the beginning of July. So at the end of June, I'm going to measure the water level in my reservoir. At the end of June, I'm going to measure the water level in my reservoir. Let's use the decision variable YB for that. And I'm also going to measure how much I'm short. Let's use decision variable ZB for that. So YB is the water that we have in our reservoir at the end of June, given that rainfall during June turned out to be low. Okay, and ZB is the amount we're short at the end of June, given that rainfall during June turned out to be low. Okay, and likewise, with node C, let's associate decision variables YC and ZC. What is YC? Amount of water that we have in our reservoir at the end of June, given that rainfall during June turned out to be high. What else? This node also corresponds to the beginning of July. At the beginning of July, I need to decide how much water to release from my reservoir during July. So this node also represents the beginning of July. So at the beginning of July, I need to decide how much water we should be releasing from our reservoir during July. So let's put a decision variable XP over here. And XP is the amount of water that we released during July, given that the state of the world is this node. XP is the amount of water that we released during July, given that rainfall during June turned out to be low. And let's also put XC here. Again, this is the amount of water that we released during July, given that state of the world is over here. X is the amount of water that we released during July, given that the rainfall during June turned out to be high. Good. That takes us to the end of July. At the end of July, I'm going to measure the water level in my reservoir. I'm going to measure the amount short in my reservoir. What is YD? YD is the water level at the end of July. YD is the water level at the end of July, given that rainfall during July turned out to be low, and the rainfall during June turned out to be low. Okay. And ZD is the amount we're short at the end of July, given that rainfall during July turned out to be low, and the rainfall during June turned out to be low. And likewise, YE, ZE, YF, ZF, YG, ZG. But these nodes not only correspond to the state of the world at the end of July, they also correspond to the state of the world at the beginning of August. And at the beginning of August, there is the decision I make, which is how much water I release from my reservoir during August. So now let's put a decision variable XD here. XD is the amount of water that I release during August, given that I'm in this state of the world. XD is the amount of water that I release from my reservoir during August, given that I'm in this state of the world. XD is the amount of water that I release from my reservoir during August, given that the rainfall during July was low and rainfall during June was low. And likewise, let's put a decision variable XC, XF, and XG. And this is going to take me to the end of July. Let me measure the water level in my reservoir at the end of July. ZH, YH, ZH. What is YH? YH is the water level at the end of August. Given that the rainfall during August turned out to be low, rainfall during July turned out to be low, and rainfall during June turned out to be low. YI, ZI. YJ, ZJ, YK, ZK, YL, YN, ZN, YO, ZO. What is YM? YM is the water level in my reservoir at the end of August. YM is the water level in my reservoir at the end of August. Given that rainfall during August was high, given that rainfall in YM is the water level at the end of August. Given that rainfall in August was high, rainfall in July was low, and rainfall in June was high. Okay. And do I need to make any other water release decisions at the end of August? No, the game is over at the end of August. So with these nodes, we don't associate any X decision with it. Okay. So these are all the decisions that we make. These are all decisions that we make under different states of the world at different time periods, at different months. Let's write some of these decision variables in English so that they are stuck in our head. Up, xi. Xi is the amount of water released given we are at node I. Okay, let's give an example. For example, what is XF? XF is the water that we release in August, given that rain during July was low and rain during June was high. XF is the amount of water that we released during August, given that rain during July was low and rain during June was high. Let's write that example. XF, amount of water released in August, given rainfall in July was, except the amount of water released in August, given that rainfall in July was low and rainfall in June was high. Given that rainfall in July was low and rainfall in June was high. Good. And we have these X decision variables for the nodes A, B, C, D, E, F, G. That's it. So amount of water released, given that we're at node I, so for I is equal to A to G. Okay. What is Yi? Yi is the water level in the reservoir, given that we're at node I. Let's take an example again. For example, YF. YF is the water level at the end of July, given that rainfall during July was low and rainfall during June was high. YF, water level at the end of July, given rainfall in July was low and rainfall in June was high. And last, we have and these decision variables, the yi's, are defined for the nodes A, B, C, D, E, F, G, all the way to O. I'm sorry, these y decision variables are defined for the nodes B, C, D, E, F, G, all the way to O. They're not defined for node A. These decision variables yi's are defined for the nodes Y, B, C, D, E, all the way to O. So these guys are for i's from B to O. Okay. And lastly, what other decision variable we have? We have the ZI decision variable. That's the amount we're short, given we are at node I. Again, Z decision variables, these Z decision variables are also defined for the nodes from B to O. And to give an example, let's do ZF again. ZF is the amount we're short at the end of July, given that rain during July was low and rain during June was high. ZF is the amount we're short at the end of July, given rainfall in July was low and rainfall in June was high. Good. So those are our decision variables. As we did before, now we're going to write constraints that links the water level at each state of the world to the water level in the previous state of the world and how much water we release and what the rainfall turned out to be. Let's see it again. Now we're going to write constraints that relates the water level in each state of the world to the water level in the previous state of the world, how much water we released and what the rainfall turned out to be. So now we're going to start putting together our model. Let's start by writing the objective function. Let's start writing the objective function. The revenue that we collect in node A, the amount that we release in node A is XA. For each unit of XA, we're going to make $3. So the revenue that we collect in node A is 3XA. Good. How about the revenue that we collect in node B? Well, the amount that we release in node B is XB. So for each unit that we release in node B, we're going to make $3. But what is the probability of reaching node B? The probability of reaching node B is 0.4. So then this is the expected revenue that we collect in node B. Okay. What is the revenue that we collect in C? What is the revenue that we collect in node C? The water that we release in node C is XC, so the revenue that we collect is 3XC, but the probability of reaching node C is 0.6. So this is the expected revenue that we collect in node C. What is the expected revenue that we collect in node D? Well, we're releasing XT units, so 3 times XT is the revenue that we collect in node D. What is the probability of reaching node D? You gotta have low rainfall in June and low rainfall in July. Let's say it again. What is the probability of reaching node D? To reach node D, we gotta have low rainfall in June and low rainfall in July. So then the probability of reaching node D is 0.4 and another 0.4 here. There is that. Let's write down the revenue that we collect in node D, 3XC. But what is the probability of reaching node D? Low rainfall and a high low rainfall in June and a high rainfall in July. 0.3 times 0.6. Let's keep writing all the other revenues. The revenue that we collect in node F is 3 times XF. Probability of reaching node F is 0.6 times 0.4. Multiply. Node G. Probability of reaching node G is 0.6 times 0.6. So this is all the revenues that we collect. So now on top of this, let's write down the penalty cost that we incur. Minus. The penalty cost that we incur in node B. Well, the amount we're short in node B is ZB. What is the probability? So then the penalty cost that we incur in node B is 5 times ZB, but the probability of reaching node B is 0.4. So this is the penalty cost that we incur in node B. Let's write down the penalty cost that we incur in node Z. Well, the penalty cost that we incur in node C is 5 times ZC. The probability of reaching node C is 0.6. So this is the expected penalty cost that we incur in node C. Let's write down the penalty cost that we incur in node D. What do we have? 5 times ZD. But the probability of reaching node D is 0.4 times 0.4. Low rainfall and low rainfall. Good. Penalty cost in node E, 5 times ZE. Probability of reaching node E is a low rainfall and a high rainfall, so it's 0.4, another 0.6 here. Penalty cost in node F, 5ZF, and the probability of reaching node F is high rainfall and a low rainfall. High rainfall in June, low rainfall in July. And probability of reaching the penalty cost in node G is 5 times ZG. And in order to reach node G, I need to have high rainfall in June and high rainfall in July, which happens with probability 0.6 times 0.6. So these are the penalty costs in each one of these nodes at the bottom. Let's also write the penalty cost in each one of these nodes at the very, very, very bottom. Penalty cost in node H, 5 times ZH. The amount we're short in node H is ZH, so the penalty cost that we incur in node H is 5 times ZH. But in order to reach node H, we need to have a low rainfall in June, low rainfall in July, and low rainfall in August. So then we know to have 0.4 low rainfall in June, low rainfall in July, low rainfall in August, all multiplied. And I'm not going to write everything that's going on in between. Let's write the last one. We need to write the expected penalty cost in each one of these 8 nodes at the bottom. I'm not going to write each one of them. So let's write the last one, ZO. Penalty cost in node O. And in order to reach node O, we got to have high rainfall in June, high rainfall in July, and high rainfall in August, which happens with probabilities, which happens with probability 0.6 times 0.6 times 0.6. So this is the objective function that we would like to maximize. Expected revenue from all the water releases and expected penalty costs. Expected revenue from the water releases in June, July, and August. And then the penalty costs at the end of June, at the end of July, and at the end of August. So now let's write our constraints. Let's write our constraints. We're going to write a constraint that relates the water level in this node to the water level in this node, how much we release in this node, and the rainfall. So the water level at the end of June, given that rainfall turned out to be low during June, is given by whatever we had at the beginning of June, minus what we released during June, plus the waterfall, plus the rainfall under the low demands, under the low rainfall scenario. Okay. And to compute our shortage, just like we did before, we're going to put a constraint that says ZB is greater than or equal to 100 minus YB, and ZB is non-negative. Okay, good. So now let's also link what's happening in this node. Let's also link the water level, reservoir level in this node to the water level in the node above, how much we released and what rainfall we got. YC is given by the water level at the end of June. And this node is given by water level at the beginning of June minus how much water we released during June plus the high rainfall. Let's also compute the shortage at the end of June, given that rainfall during June turned out to be high. Good. So let's also write constraints. Let's also write constraints that link the water level in this node to the water level in this node, how much we release, and rainfall. Okay, so now this is going to be a little bit different, slightly different, but not a huge deal. Slightly different, but not a huge deal. So let me write it like how? Let me write it like how? Let's do it. So YD, the water level in node D is given by the water level in node B, YB, minus how much we released, XB, plus the raw rainfall, 125. Let's say it again. Water level in node D, YD, is given by the water level in node B, YB, minus how much release, minus XB, plus the low rainfall, 125. So then we're going to write YD is given by YB minus XB plus 125. So now the cool thing is when I compute the water level over in this node, I look at the water level as a function of my decision variable in this node. Okay, good. So then we also can, so this is YB, XB. So we can also compute the shortage in node D as a function of D. Okay. And similarly, when I compute the water level in node D, E, we're going to look at the water level in node B minus how much we release in node B plus the high rainfall. YE is given by how much water we had in node B, how much we release in node B, plus the high rainfall, and the shortage in node E is 100 minus the water level in node E, and shortage in node E is non-negative. So this is happening with level 3 nodes, level 1, level 2, level 3 nodes. Let me not write the other 2 level 3 nodes. So let's say similarly for other level 3 nodes. So these constraints were for level 3 nodes. Okay. Now let's write our constraints for level 4 nodes. Water level in node H is given by the water level in node D minus how much we released on node D plus the low rainfall. Water level in node H is given by the water level in node D minus how much we released on node D plus the low rainfall. YH is given by the water level in node D minus how much we release in node D plus the low rainfall. Okay. And likewise, let's compute the shortage. And shortage in node H is non-negative. Let's do one more node in the fourth level. Water level in node I is given by how much water level we had in node D, how much we released in node D, plus the high rainfall. Water level in node I is whatever we had in node D, minus how much we released on node D, plus the high fall. Let's also compute the shortage, so on and so forth. And similarly, let's say for other level 4 nodes. So these are the constraints for level 4 nodes. And these are the constraints for level 2, as you realized. Good. Okay, so now we can put our optimization problem together. In our optimization problem, we're going to maximize this objective function subject to all of these constraints. We're going to maximize our objective function subject to all of these constraints. Let's write this down so that we have a full formulation of our optimization problem. Maximize this humongous objective function. 3xa plus 0.4 times 3xb plus 0.6 times 3 times xc plus 0.4 times 0.4 times 3 times xd plus 0.4 times 0.6 times 3 times xc 3 times xc plus 0.6 times 0.4 times 3 times xf plus 0.6 times 0.6 times 3 times xg. So these are my revenues. Let's write our costs. 0.5 times 5 times zb minus 0.6 times 5 times zc minus 0.4 times 0.5 times zd 0.4 times 0.4 times 5 times zd minus 0.4 times 0.6 times 5 times ze minus 0.6 0.4 5 times zf minus 0.6 0.6 5 times zg. We took care of these numbers. And lastly, let's write down the penalty cost that we incur from all the bottom level nodes, from all of these 8 bottom level nodes. Those are too many to write, but let's just write a few of them. ZO. Okay. This is our objective function that we want to maximize. Good. Let's write our constraints. I'm going to write the same constraints. But let's write these constraints from scratch together, so that again, we got good exercise out of this. Subject to the constraints. What is our first constraint? We're going to compute the water level in this node B as a function of the water level here and how much we release and rainfall. YB is given by 150 minus XA plus low rainfall. Good. And then let's also write the shortage quantity in node B. CB is greater than or equal to 100 minus YB. And we're going to write the non-negativity constraint for ZB later on down the road at the very bottom. Let's compute the water level in this node as a function of the water level at this node, how much we release and the high rainfall. YC is given by 150 minus XA plus high rainfall. And ZC is greater than or equal to 100 minus YC. So we took care of what's going on with these nodes and this level. Okay. Good. So now we took care of node B, node C. So now let's take care of these nodes. These are the nodes that are at level 3. Let's take care of the nodes in level 3. YD is given by, for the water level in node D is given by water level in node B, minus how much we release, plus the low rainfall. And shortage in node D is greater or equal to 100 minus YD. Good. And now we're going to write one of these constraints for every node in level 3. And let's jump to the last node in level 3, which is the G node in level 3. YG is given by the water level in the node YC plus how much release in node C plus the high rainfall 300. And ZG is greater or equal to 100 minus YG. So these are the constraints for level 3 nodes. Okay. Let's write the constraints for level 4. Let's write the constraints for level 4. YH, the water level in node H, is given by water level in node D minus how much release plus low rainfall. Water level in node H is water level in node D minus how much we release in node D plus the low rainfall. And again, shortage in node H, ZH, is greater or equal to 100 minus YH. And let's finally write the last node in level 4. Let's write the last node in level 4. What's happening with the last node in level 4? Right over here. Dot, dot, dot. The water level in node O is given by the water level in node G minus how much we release in node G plus the high rainfall. And then the shortage in node O is greater than or equal to 100 minus YO. Okay. So these are our constraints for the level 4 nodes. Okay. And this is level 2 if you like. Okay. And all of our decision variables are non-negative. So this is a colossal optimization problem. It's a colossal optimization problem. Once we solve this optimization problem, the decision variables for x's are going to tell me how much water to release under every possible state of the world. And the decision variables y's are going to tell me what the water level is going to be under every possible state of the world. And the decision variables z's are going to tell me the amount I'm short under every possible state of the world. So let's say the optimal value of the decision variable, I'm making it up. Let's say the optimal value of the decision variable xc came out to be 100. Let's say the optimal value of decision variable xc came out to be 100. That means that if I'm at the beginning of August and rainfall during July turned out to be high and rainfall during June turned out to be low, if I'm at the beginning of August and rainfall during July turned out to be high and rainfall during June turned out to be low, then you got to release 100 units of water during August. Okay? And let's say we solve this colossal linear program and the value of the decision variable xg came out to be 300. Let's say the value of the decision variable xg in the optimal solution came out to be 300. That means that if the rainfall during June was high, and if the rainfall during July was high, then in August we should be releasing 300 units of water. Okay, so then the values of the x decision variables will tell me under every possible state of the world how much water to release. And likewise, if the optimal value of the decision variable xc came out to be 250, it means that if the rainfall during June came out to be high, then we should be releasing 250 units of water during July. If the decision variable came out to be, if the decision variable xd came out to be 125, it means that if the rainfall during June was low and during July was low, then during August we should be releasing 150. Okay. So this is how the solution to this big linear program captures the decisions that we should be making under every possible state of the world. And this is the big colossal linear program that we end up with. So let's say a few things about this. This kind of a scenario tree would go very, very large if you're looking at a large number of time periods or the number of possible realizations of the random quantities is quite a few. So this kind of a scenario tree would get very, very large. So you got to be careful about using this kind of an approach in general. So let's go into the wrap-up mode. So in this lecture, we saw how we can model decision-making problems under uncertainty when we're making decisions sequentially. And as we make the decisions sequentially, uncertain quantities are revealed to us. Okay, so this is one way of modeling these problems. And as I said a minute ago, this way of modeling the problems may give us scenario trees that are extremely large. Okay, so you got to be careful when you use this kind of a modeling approach. Nevertheless, this way of modeling the decision-making problem under uncertainty essentially allows us to model everything by using the standard linear programming framework. So we did not have to learn anything new, right? By using the standard linear programming framework, we saw how we could incorporate some uncertainty into our decision-making problems. We do not need to learn anything new. But nevertheless, again, when you're looking at a problem where there's a lot of different realizations of the uncertainty, and there are many different stages where we make the decisions, then the scenario tree can get very, very large, very, very quickly. So we got to be careful. But the advantage of this is we do not have to learn anything new. We could just fit everything into the standard linear programming framework. Okay, so this is a good point to stop. So now we have one approach at least to handle uncertainty in our optimization problems. The field of decision-making uncertainty is vast. What we've seen in this lecture is only one approach, but again, this allows us to use the standard linear programming framework. Great, let's stop here.